this up again. What did you guys learn about Hamiltonians in 102?
We talked about Hamiltonian.
You didn't talk about it? Okay. Good. Sometimes they do. Might come later. Guys, you talked a bit about quantum mechanics?
I think so far, all that's been mentioned in regards to the Hamiltonian is that there's one problem where it gives you a useful result.
Oh, that's all. Okay.
Something.
Okay, well, we'll be ahead of the game that way. We'll be ahead of the curve. Okay, so to do Hamiltonian mechanics, you have to have Lagrangian mechanics. I'm just going to write Hamilton here, and I'll just remind us of those steps. So the first thing is you have to look at your mechanical system and set it up and construct the Lagrangian. So you need Lagrangian for the mechanical system. So this is a branch of mechanics you could not have studied without knowing. And so L of Q1 to Qn, I'll go ahead and write them all out. Q1 dot to Qn dot and T if it's explicitly among the time. Okay, so you have to go through those steps, and as we've seen before, that can take a bit of doing as well as constructing the Lagrangian. Then you define piece of I dl dqi dot. And what is that? That's the generalized momentum that we've often seen. And you guys remember, if Q is cyclic, this thing is conserved. Right? But I'm just going to write the generalized momentum. And the goal of the Hamilton mechanics is to get the generalized momentum. So you've got that. The third step is to form the energy dl qi dot minus L. L is right up here. And the thing to do is to express it in terms of Q and P. So express this thing in terms of Q and P. I'll just write Q, P. And if you can do that, that is the Hamiltonian Q1 to Qn, P1 to Pn, and T. If you can do that, and this is an algebraic task right here. This is purely an algebraic problem. You have to conquer that problem. Then you have the Hamiltonian. Over here, it's just the energy. It's still the energy, but it's now expressed in terms of coordinates and momentum. And if you get there, the new question is, what are the equations of motion? Okay, they're no longer the Euler-Lagrange equation. And so I'll put here equations of motion are actually up here on the board. The equations of motion are qi dot equals dh dpi and pi dot equals minus dh dqi. And these are called the canonical equations. And I think we did one example, and if you do the construction, go through this and keep going, you end up where you started. Come full circle, that's just a condenser. But there are other benefits of this method of mechanics besides just solving the equations of motion. But yeah, these are the new equations of motion. You notice they look really symmetrical, except one of them has a minus sign. The way to remember which one has a minus sign is, this is actually Newton's law. Because v dot time derivative of the momentum is equal to minus the gradient of what turns out to be the potential. So this is the one that gives you Newton's law in the appropriate case. Newton. Okay. This is the one that has a minus sign. So I have a major problem for you guys. And we found Hamiltonians. I think if you look in your notes, what did we have? Projectile motion. Did we do the central force one yet? No, we didn't. We just did projectile motion and a simple one. Okay, that's good. That's a good start. So yeah, what we're gonna do next is I'll do the central force Hamiltonian, and I'll let you guys do the. Good. Yeah, I got a good idea here. Actually, we don't have this list up here, but I wrote it too big, so I got to erase it. But yeah, we're just gonna go through these steps. Yeah. How about this? So next, Hamiltonian or plane polar coordinates. So this is a bit more general than the central force, that we can do a little bit more. So our first step, L is a half m r dot squared plus a half m v dot squared minus u of r and p. So that's our first step, and by hook or by crook, we get the Lagrangian, there it is. And then the second step, we have p sub r dl dr dot, and that is m r dot. Okay. So the definition, dl dr dot, and if I go here, I see it's just m r dot. Okay. And I'm also going to do p sub phi, and then I'm doing the derivative over here, dl phi dot equals m r squared phi dot. Okay, who recognizes p sub phi from another life? When we did the central force problem, what was this thing called? Here's the angular momentum, right? So in this case, the generalized momentum is angular momentum. And now we construct the energy. So the energy is, and you know, we've done this before, but I'm going to do this r dot minus L. So we have m r dot squared plus m r squared p dot squared minus 1/2 r squared p dot squared. And this is pretty stereotypical. You've got the thing, you're taking off 1/2 of it. Minus and negative is plus u of r and p. So yeah, this energy really just turns into T plus U. So we're going through all the steps this time. R squared P dot squared plus U of R and P. So this is H now. No, this is E. Okay, so that's the energy. So how do we turn this thing into the Hamiltonian?
R dot and V dot, right?
Precisely. So now we substitute in, so I'm going to go ahead and write H. I've got a half, I've got M, the R dot is P sub R over M plus a half M R squared, and the P dot is P sub phi over M R squared, square that. And that will will give us, I'll write it this way. So now we have p sub r squared, 2m plus p squared over 2m r squared plus u of r and p is equal to e. Oh, sorry, is equal to h. Okay, let me write it this way. H equals, that was the energy, but now it's also the Hamiltonian. And notice the variables we have here. Function of r and phi, p sub r and p sub phi. And yeah, if you could do the equation of motion, and if you take them far enough, you're going to get the same things as the Euler-Lagrange equations. Okay. But yeah, there's your Hamiltonian. So I'll add as a homework problem. So we have so far the things on the exam there we have construct, now we have construct H for spherical polar coordinates. So we have that there. This one will take a little bit of extra doing. If I had asked you for the Hamiltonian for cylindrical coordinates, we should just be able to do it by inspection. What do you guys think?
I mean, we should just be able to add a couple terms onto our Hamiltonian here, right? Spherical coordinates is just you extend your plane polar upwards, z.
And the one that you extend with z, that's just the Cartesian coordinate. So because it's Cartesian, we would just do pz squared over 2m, right? And u of r, phi, and z. And we might change the letter r to rho, but that would be, so I won't assign that one, but let's just put a note here. H, Hamiltonian for cylindrical coordinates. Equals question mark, and then, go down there and extend the concept. Now with the plane polar coordinates, what's the difference between this and the central force Hamiltonian? Say the same thing up here. What's the difference between this and the central force Lagrangian? You guys notice? Go back to your hand. Anybody?
Our potential goes to depend on the angle.
That's right. For the central force, potential doesn't depend on the angle. Remember the Kepler problem was just line south over r, that kind of thing. So we can immediately get the central force Hamiltonian. What can I erase? This stuff up here? We have this? Yeah. So yeah, we'll get the central force Hamiltonian. It's a good place to end. It's a perfect place to end. So this was Hamiltonian for plane polar coordinates. Central force means that u is not explicitly a function of phi, right? U is just u of r And what does that mean in the Lagrangian? That means that BL BP dot not so fast. It means that d over dt BL BP dot is equal to 0, and that was a conservation of angular momentum. Okay. L was BL BP dot was a constant. What about the Hamilton equation of motion? So next we have P sub phi dot equals dH dT with a minus sign. That's the Hamilton equations. P dot equals minus dH dQi, right, just like that, equals 0. That means P sub phi is equal to a constant. And we're gonna name it alpha. There's some tradition in Hamiltonian mechanics that they name things alpha. Alpha sub I. With Hamiltonian mechanics, we can take this conserved quantity back into here. We take it back in here, and it'll be in there as a parameter. So watch this. Now, H equals, it's gonna be H of R, P sub R, semicolon alpha. Alpha is just a parameter. And so we'll say we have P sub R squared over 2m plus alpha squared over 2mr squared plus Q of R. So this here is the punchline. This is really important. Where have we seen this thing before? In a different lifetime. We used to call this L. Remember we had L squared over 2m squared plus Q of R. That was the effective potential, right? So when we solved the Kepler problem, central force work we did, we actually had gone to this transformation over to the energy and then continued on our way without knowing that it was Hamiltonian mechanics. The reason is, if you plug this constant phi dot in here, you no longer have a legitimate Lagrangian. You'll actually get the wrong equations of motion. So when you make that, when you evaluate the conserved quantities and continue on with your solutions, you actually have to go to the energy. And we did, right? When we did this back in last semester central force problem, we actually used the energy. Okay? So anyway, I think I'll leave it right there. We've got some problems for next week, and we just made contact with a bunch of stuff we've done before with the Hamiltonian method. So this was, I should note here, this whole topic was cyclic coordinates. And we should probably start with cyclic coordinates next time, specifically, but that's what we were discussing right here, cyclic coordinates. Okay, good.